All right, welcome everyone. Today we're going to continue with some of the theorems, okay, one theorem in particular with our vector calculus, how we can kind of toggle between, we can jump between these line integrals and now our surface integrals. We saw something similar to this kind of conversion when we dealt with Green's theorem previously. So now this is kind of an extension of that, if you will, more multi-dimensional feature where we're going to relate a line integral and a surface integral, okay? All right, so let's go ahead, share the doc cam, and we'll get going with that work. All right, so now with this theorem, Stokes theorem, and again, what this is doing for us, this is a way of rewriting, converting between a line integral and a surface integral. Because depending on our surface, depending on that path, this line that we want to integrate over, it may be beneficial to rewrite easier to convert to compute a line integral as compared to a surface integral, or vice versa, easier to evaluate a surface integral than it is the line integral. Okay, thinking about those line integrals, we have like these kind of jagged boundaries where we may have to separate into these different pieces. It may be easier just to work with the surface and integrate compared to the separate integrals of our boundary. Okay, so let's bring in the statement, and then we'll hopefully break down that theorem and, more importantly, see some examples. Okay, so Stokes' theorem says we're going to let S be an oriented, right? So we want to keep that kind of positive orientation. Think of the normal vector pointing out from the surface. Piecewise smooth, right? So these portions of that surface have defined derivative, continuous. Okay, piecewise smooth surface that is bounded by a simple, right? So no loops over itself, closed, right? So our initial point and our terminal point match up. Piecewise smooth again, right? So again, our derivatives hold for our boundary, continuity holds. All right, so piecewise smooth boundary curve C with positive orientation, right? So we're going to go around that closed loop, that closed boundary, counterclockwise, okay? There's that setup. So let's let F be a vector field whose components have continuous partial derivatives. Right, so all this setup on an open region. In our three-dimensional field that contains S. All right, so this vector field will be continuous partial derivatives in all that space where we evaluate wherever S resides. Then, now here's the theorem statement. Then what we can do, we can take this line integral of our vector field over the closed boundary, And we can equate it. It's the same as the surface integral of our curl of f dotted with ds. And we can go back and forth. We can take a line integral, convert to a surface integral, or vice versa, take a surface integral and jump back to a line integral. Okay? And what this concept is that if we're dealing with some surface S, okay, we could imagine going through that work with a surface integral, taking those little bits of ds, right? That curl of f being that del cross f, getting that result. Okay. And then when we see this integral, we can do our surface integral work that we saw in our text 16.7. Or likewise, maybe the surface is going to be kind of elaborate to manage. We see some difficult expressions, if you will, involved with that curl f. So maybe instead, if we can find a way to parameterize more succinctly that boundary C, we can deal with the line integral of C of that f dotted with dr, right? And this becomes kind of that f dotted with that r prime dt, and we can go through that work. Our line integrals, which I believe we did in 16.2 or 16.3 of our text. And so depending, it may be easier to evaluate a line integral than it would be a surface integral, and vice versa, rather than having kind of a, most likely these kind of boundaries that are different segments and having to add up all those different calculations. Maybe we can just work with that particular surface, the curl of f, maybe not too terrible, and making that integration a little bit simpler. Okay, all right. And so an interesting part about this, though, okay, something interesting to note with that work is that for some complex surfaces, that boundary may be easier to consider, to work with. Okay, but also an interesting note, surfaces with the same boundary can be simplified to the same interval. Right? Because imagine that if we have this as our surface, this kind of weird bubble, if you will, okay? Imagine like this three-dimensional bubble. right? But with the boundary, this kind of lower edge, and a kind of circle that we can work on. But then taking that, and then maybe if we just have in a second, let's call this S sub 1, like this first surface, okay? But maybe in another surface, we have like a paraboloid. But it still shares the same kind of boundary, that circle. But now in this case, this S sub 2 maybe a paraboloid. But as long as these two share the same boundary, what Stokes' theorem provides us is that even if I was to do this surface integral over that surface of that curl f dotted with ds by Stokes' theorem, this is going to be the same as the integral, the line integral over that closed boundary, that circle. We're using the same vector field f dotted with dr here, parameterizing there. But this would give us the same as this surface integral of the curl f dotted with ds. Since they both share the same boundary, these two integrals, right, with that vector field acting to them, would be the same, which is kind of interesting to simplify down, right, in terms of that writing. So the big part we can see is kind of creating that boundary and recognizing to kind of alleviate, in certain cases, the work of the surface. All right. But let's look at some examples. All right, so here we go. And so typically when we see these problems, it'll say, okay, use or apply Stokes' theorem to evaluate, and they give you one form of the integral, and that just means Stokes' theorem to use the opposite, right? So in this case, it asks us to use Stokes' theorem to evaluate the surface integral, the integral over the surface S of the curl of f dot ds. Okay, and so in that case, when we see that statement, use Stokes' theorem to evaluate here. This means do the other form of the integral. So in this case, since we were given a surface integral, we're going to want to convert to a line integral, which is the integral over that closed path C of f dotted with dr, right? So in that case, what we're going to need to do, we need r of t for the boundary, and we're going to need r prime of t for our integral, right? Because when we've done this before, calculating back when we get our limits, we're going to go f of r of t dotted with r prime of t dt, and our t parameterization, sorry for the wobbling there, goes between a and b. There we go. All right, so there's that big dump of information that kind of, okay, this is what we're going to be doing. So now let's see this problem, and we're going to check out problem number 4. This is on page 1179 from our text. Our vector field F of x, y, z is this arc tangent of x squared, y, z squared for the I component, plus x squared y for the j, plus x squared z squared for the k, right? And so you can imagine if we're dealing with our surface integral, the given format, that curl of f, we'd have to find that partial, or we have to do the cross product. That's going to involve taking these partials with respect to x or y or z, right? With that arc tangent, that inverse tangent, which not impossible, but it just gets messy, especially since we have all these products going on, depending on which we're taking with respect to x or y or z. It'll definitely become a little bit daunting having to maneuver those components. So since that kind of curl, I'm guessing is going to look pretty difficult. They're more complex than I want to manage. Maybe if we can find a boundary, which I'll write up in just a second, this line integral taking these components may simplify down a little bit better, a little bit easier. All right, and so then now what they're talking about, S is the cone, x is equal to the square root y squared plus z squared. X is going to be between 0 and 2, oriented in the direction of the positive x-axis. Okay, so it's kind of giving us where that point of our orientation, right, where we're going to be facing when we're standing on that surface would be. Okay, and so again, if we're thinking about this cone, x equals the square root y squared plus z squared, it's a cone opening along the x-axis, right? Positive, so it's going to be positive x values. If we were to kind of think about those traces, those level curves, letting z be 0, for instance, x is equal to square root of y squared is y, x equals y. We're going to get that line kind of outwards. Likewise, if we let y be 0, x equals the square root of z squared, x equals z. So we're going to get this kind of line. And then it's this cone, so it's going to sweep down like so. I could be better about that. And it's kind of going out until x is 2. So we're going to get this cone opening along that x-axis, right? The idea is, well, instead of having that cone, let's just look at this boundary curve, right? That curve where the cone kind of emanates from there. Here's our boundary, this circle at x is equal to 2, right? X is always 2. That's where we're slicing off. But then let's think about that circle, right? So on that span, if we imagine just a y, z plane, projecting that down or kind of thinking, okay, I'm going to bring this axis up to reside at that x equals 2, fixed here, fixed location. What is that circle going to be, right? Well, when x equals 2, 2 is equal to the square root of y squared plus z squared. Y squared plus z squared is equal to 4. It's a circle with radius 2. So this is what, again, our boundary looks like. And again, we want to traverse this in the positive orientation, counterclockwise. So just like we would think about with our polar coordinates before, these circles. Now, instead of having x and y, we have y and z. So in this case, my y is equal to the radius cosine theta, or in this case, our radius is 2 cosine theta. Z is our sine theta, or 2 sine theta, right? We're fixed at x equals 2. Or we can do t, right? But with all that identified, what we're going to find then for our boundary C, we're going to make this R of theta. We can do R of t if you like. The x is 2, the y 2 cosine theta, the z 2 sine theta. Okay? R prime of theta. All right, taking the derivative of theta, right? Before we might have used a t, 0, negative 2 sine theta, positive 2 cosine theta, and on the side is d theta outside. Oh, let me put that on later, sorry. That's accurate here, okay? And so what happens, that surface integral that we had been asked to compute with for previously with now Stokes theorem, this is going to be equal to this line integral over C, f of r, now a theta, dotted r prime of theta d theta. And now for our entire circle, notice what we have. We have r theta between 0 and 2 pi, right? We want the entire circle for our boundary is not just in that first octant, first quadrant. So we're going to go from 0 to 2 pi. So this integral becomes the integral from 0 to 2 pi. And now let's think about some of these pieces, okay? So if our function off to the side here, my f originally inverse tangent x squared y z squared x squared y x squared z squared, we're going to have to plug in what that r of theta is going to do, right? The x, y, and z components. But plugging that into my inverse tangent, I know it's going to be kind of messy for a moment. So let me first kind of use this notation, and I'm going to convert to that theta format afterwards, okay? Because I'm going to dot this with my r prime, 0, negative 2 sine theta, positive 2 cosine theta, and then let me not forget my d theta, okay? But the reason I wanted to kind of take that action first is because now when I do my dot product, I'm going to get that 0. So I don't have to worry about that inverse tangent at all. But now these I'm going to definitely have to consider, right? Because now when I multiply here, I'm going to get plus that x squared y has negative 2 sine theta, plus, and then lastly, x squared z squared times that 2 cosine theta. And we still have that d theta at the end there. So as I start to go through, now x squared, y squared, with our rewriting, that's going to be 2 squared 2 cosine theta times this negative 2 sine theta plus, and now here, x squared 2 squared z squared, which was 2 sine theta squared, times that 2 cosine theta, all d theta still. And so then here, 0 to 2 pi. 2 squared is 4, times 2 is 8. I'm going to 2, 16, negative 16 cosine theta, sine theta. 2 squared is 4. 2 squared is another 4. 4 times 4 is 16, times 2 plus 32 sine squared theta, cosine theta, all that d theta. So integrating here, u sub for this one, u sub here as well, and we can evaluate, okay? And I'll let that be to you. I'll remember to write a final solution. I think it comes out to be 0 in the end, okay? Which has been kind of interesting result. It's not always going to be 0. We might get a real number result here, but just kind of seeing that progression is still tedious in terms of having to plug in these components. But instead of having to deal with the curl of this vector field, once we identify that boundary, we can convert that surface integral to this line integral. The boundary is a lot easier to manage, parameterize it, whether you want to do thetas, t's, whatever, simply you like. Do that dot product, f dotted with that r prime, and that's hopefully a much simpler integral, okay? So again, when we're given one format and it says use Stokes theorem, it just is okay, now rewrite it as that other format. So this one we went from a surface integral into a line integral. Let's go the other direction now with our next example, okay? All right, so now for this next one, let's look at this example. Let's try number 8. We did number 4 previously. Now number 8, page 11, 1179. Again, use Stokes theorem. To evaluate this line integral, the line integral f dotted with dr, our vector field dotted with dr. And again, in each case, we're going to assume that C is oriented in the counterclockwise direction as viewed above. Okay, and so jumping to it, this time our integral of this f dotted with dr, our f, x, y, and z is equal to 1I plus x plus y, yz j plus xy minus the square root of z for the k component. And then C is the boundary of the part of the plane (3x plus 2y plus z is equal to 1), in the first octant. Okay. All right, so let's first check out this plane. Okay. We're in the first octant, right? So all positive values for X, Y, and Z. So when I graph that plane in our first octant, I basically just take the time to say, okay, well, let's wait and see what happens when we let these different coordinate variables be equal to 0. Right? So when X equals 0, we're in the YZ plane. 2y plus z is equal to 1, or z is equal to negative 2y plus 1, right? So we can imagine if z starting at 1, the slope down 2 over 1, we're going to come over here to a half along that y-axis, right? And again, you can double check where am I, when z equals 0, where we're crossing that y-axis, or when z and x equals 0, y is going to be 1/2. Similar, when y equals 0, 3x plus z is equal to 1, or z is equal to negative 3x plus 1. So again, starting off with that z intercept at 1. Now we go down 3 over 1. So in this case, a little bit shorter. My scaling a little bit off, but we're going to cut down here to 1/3. And again, you can check when z equals 0, y equals 1, or x equals 1/3, pardon me. And then we can even do that last plane when z equals 0, 3x plus 2y equals 1, y equals negative 3/2 plus 1/2. And you'll see right at that plane, it should connect those points. All right, so there's this plane, part of the plane in the first octant. And as we start to go through it, if we start to go around that counterclockwise direction, you might see that we'd have to go through 3 different paths for that boundary, for that line. Okay? Not terrible, but just some work in having to parameterize for each. Okay? So what Stokes' theorem says, instead of having to separate into those 3 different intervals, instead, we can convert this to a surface integral, taking the curl of f dotted with ds now, where our surface that we're dealing with is that plane, okay? And so for that plane, (3x plus 2y plus z equals 1), the same thing as having z equals 1 minus 3x minus 2y, what we had back in surface integral discussion lecture, that can be our g of x, y, z. We parameterize in terms of x and y. And this integral over that region S, what we can do instead, let's call it this region D. And what we had gone through with that section 16.7 before, okay, when we had gone through that work previously, we had done this. I'm going to keep my curl of f, but that ds was that r sub x cross r sub y dA. And then one of those formulas we had done, if this curl is like our PQR, we can dot it with negative dg dx, negative dg dy, positive r. Okay, and we have our dA component. And let's do that work. So you value this cross product. This is in section 16.7. We have gone through that process. Okay, and so with that in mind, let's look at that surface integral, right? So in this case, if f was equal to 1 x plus y z, xy minus root z, okay, then my curl of f, that cross product of our grad, right, our del operator, d dx, d dy, d dz, that operation with our vector field f, taking that cross product. So in terms of the I component, cross out that column, that row, derivative with respect to y of x, y minus z. The z is a constant 0. We get x. Derivative here with respect to z, that x is a constant, it goes away. Derivative yz, by a constant sticks around. It's minus that derivative, so it's going to be minus y. Now for the j component, that column, that row, d dx of xy minus root z, we get here y. Derivative of 1 with respect to z, 0. And then lastly, the k component, last column, top row, d dx of x plus yz, yz constant, so we just get a 1. Derivative of the constant with respect to y, 0. So in this case, our curl of that vector field f, x minus y, negative y, 1. And these are these values we're going to call P, Q, R. And so this surface integral of that curl f dotted ds is going to be this integral of our over this region from our domain, curl f dotted with that negative dg dx, negative dg dy, 1 dA. And again, I mentioned this before, if we look at equation 10 in 16.7, 16.7.10, we have that component identified, how we got to that result, okay? And so for us, our z was g of xy, which was that plane, 1 minus 3x minus 2y. So dz dx or dg dx, negative 3. dz dy or dg dy, negative 2. Okay. Looking back at that plane that we had identified before, I know my color scheme a little bit different here, but this was 1/2, this was 1/3. the region D of which we're integrating, right? If this is my plane, I'm taking these points from my xy plane, sending it to that function to get the plane, right? So there's my region D. And how would we organize this? We can say that x goes between 0 to 1/3. The y goes from 0. This is y, this is x, this is z. The y goes from 0 up to this line. And remember from our plane work before, how we got this little boundary line before, this was that y equals negative 3 halves x plus 1/2. And that's that line. So this gives us our boundaries, our limits for our double integral here, for our that area integral. And so in this case, this becomes this integral. The curl of f we had done, x minus y, negative y1, dotting dg or negative dg dx negative of negative 3, negative of dg dy, negative 2. That last term is a 1. And depending on how to organize, since y depends on x for that boundary, I'm going to go dy first, dx. I'm going to go from 0 to negative 3 halves x plus 1/2, 0 to 1/3 for the x. And again, as we go through, doing that dot product, negative of negative 3, positive 3, 3 times x minus y, negative, negative, positive, 2 times negative y, and then plus 1, y dx. And of course, we can combine like terms here and start to evaluate. Okay, but I'll leave it at that for now. That setup, of course, some time to think about, but hopefully a lot better than having to create that line integral with 3 different boundary lanes. Okay, so that's the use of Stokes theorem, converting, right, the surface integrals into line integrals, or vice versa, line integrals into surface integrals. All right.